as far as announcements are concerned. First and foremost, we have, so we're going to be nearing the end of chapter 3 today. We might have a little bit as far as periodic trends to cover in Monday's lecture, but we're going to cover the primary trend today at minimum, which is atomic size. And most of the other periodic trends that exist can be derived from atomic size. So I'm going to keep that post-lecture due Sunday for periodic trends. If we need to talk a little bit more about it on Monday, we have that option. But I'd like to use Monday primarily as a review day. So what I want from you is go through those post lectures, go through your notes over the weekend, identify some trouble spots, some things where you're a little bit unsure of things, and we will talk about them on Monday. Monday, I'll also give you a bit of a preview of the quiz, let you kind of know what to expect and what kinds of questions to expect. So those are the post lectures due over the weekend. Chapter 3 homework and quiz are due on Tuesday. Chapter 3 homework is now available in SmartWork, so you should be able to access it. It's a 27-point assignment that you have 31 points possible for. So again, some rolled in bonus there if you're willing to do a couple of extra problems. Speaking of bonus, as part of the preparation for the nomenclature bonus day, so nomenclature bonus proficiency is due on October 4th. That is 2 weeks from this coming Sunday. To help prep for that, there is a bonus lecture in GradeScope on nomenclature. So in it, it's like a lot of your other post lectures. I give you information, I give you some practice problems to work on, and essentially the practice problems are bonus. It's all bonus. So forget the exact total. It's either 8 or 10 points of bonus that you can earn by doing this extra activity. And that extra activity is also due on October 4th. So it coincides with the bonus deadline because I'm trying to kind of set up the idea that October 4th is basically bonus day. Post lecture for bonus. And if you pass the proficiency by the 4th, you get bonus points there as well. So that's what we're kind of looking at as far as the week ahead is concerned. Any questions? So going back to where we left off on Wednesday then. Wednesday, we had just completed complete and noble gas configurations for electrons in atoms. We're going to finish that conversation by first talking about some anomalies. And what do we mean by anomalies? We mean places where there are exceptions to our rules. And in particular, we're going to talk about 2 different kinds of exceptions. Both of these exceptions involve the D block of elements. So there are some F block exceptions, but again, we're not going to get into the F block exceptions because A, there are too many of them. B, they're kind of random. There's no real set order about them. And C, we're not going to do a whole lot of chemistry of rare earth elements anyway. So what are these exceptions? Well, we see that we've got a number of transition metals here: copper, silver, gold, platinum, rhodium, ruthenium, chromium, molybdenum, niobium, and palladium. What do these words mean, S1 and S0? Well, this is telling us how the exception is going to occur. In both sets of these exceptions, what we're going to see is an S electron move over to the D sublevel. Now, why does it do this? Stability. By moving an electron from the S into the D, it's creating a more stable D sublevel, which is lowering the energy of the atom as a whole. And so in the S1 exceptions, we would see one electron move over, and I would be left with one in the S sublevel and plus one more in the D sublevel. And for palladium, we actually see S0. So for palladium, and palladium's the only one that does this, I have my 5s sublevel and my 4d sublevel next to it. And if I look at the configuration of palladium as it sits normally, what I would see is that I have 5s2, 4d8 for palladium. What happens is that both of these electrons migrate over. The end result is 5s0, 4d10. So something's happening in the palladium where filling that D sublevel actually creates a more stable state than having that S sublevel filled. Now, palladium is the only one that does this. Now, one thing about this does look like just a random list of elements. However, what we will see is that there is some rhyme and reason to the exceptions. So for the S1 exceptions, I'm going to code them in red here. If I plot them out on the periodic table, those are my S1 exceptions. And in particular, I want to highlight two of these groups. Group 6B, otherwise known as the D4 configuration, and group 1B, otherwise known as the D9 configuration. Why are these ones important? Well, again, we got to come back to Hund's rule. Hund's rule says that those those orbitals in that sublevel are degenerate. If I have a D4 configuration, I've got 4 electrons in 5 orbitals. Adding a 5th stabilizes the sublevel by giving 1 electron in each orbital. So for chromium and molybdenum, the move from D4 to D5 makes some sense. For the D9s, we've got a similar kind of argument. D9 would have this configuration. Adding one more electron would give it a D10 configuration. So we would go from a mostly full sublevel to a completely full sublevel. And again, we're going to gain some stability in doing so. So for 5 of the 9 exceptions in the S1 block, we can rationalize their decision. We can rationalize why the electrons go the way that they go. The other ones, yeah, you gotta kind of just go on faith a little bit there. Something weird about the 4D block. A lot of our exceptions in that 4D row. What we do find is that 5s and 4D, as far as energetics are concerned, 5s and 4D are very, very close to each other. And so, since they are so close to each other, it's not that uncommon to see electrons jumping from one to the other because the energy gap is so small. The S0 exception we'll put here in blue. That's palladium. And again, we see palladium in the 4D sublevel as well. And so if you look at it, of the 10 elements in the 4D sublevel, 6 of them are exceptions. The ones that aren't, cadmium, which is D10, is already completely filled S, completely filled D, so there's no place for those extra electrons to go. Technetium, D5, so adding an extra electron would actually unbalance that already half-filled sublevel. And then with yttrium and zirconium, really wouldn't be an advantage. To go from D1 to D2 doesn't really increase stability all that much. To go from D2 to D3 doesn't increase stability all that much. But for the other ones, we do see, again, for some reason, that 4D sublevel, we've got very, very close energy between it and the 5s. All right, let's do some practice here just on our own. And for the purposes of time here, let's make this a little bit shorter and just do the noble gas configurations and not the complete ones as well. So there are a couple of exceptions thrown in here. Don't forget about your fundamentals. For noble gas configuration, move backwards to get to the nearest noble gas, put that noble gas in brackets, and then finish the configuration with everything that comes after that noble gas. Take a couple minutes, write out these four, and we'll come back and talk about it in, let's say, 4 minutes. So a couple of problems that I noticed walking around that we need to point out. First of all, the ordering here does matter. Now, I have seen some textbooks put them in energy level order, and so like for gold example, it would be 4F14, 5D10, 6S1. And that's okay to do, Conventional wisdom, though, tends to dictate that we actually do it in order of energy. The 5d electrons are higher energy than the 4f, which are higher in energy than the 6s, which were higher in energy than all of the electrons in xenon. So there's merits to both sides. Putting them in energy level order will help you when we start making ions, because when we make ions, the ions will be the electrons will be subtracted from those higher energy level sublevels rather than the higher energy electrons because of a distance thing. The further away from they are from the nucleus, the easier they are to remove. The other thing I was pointing out as I walked around, remember, 6th energy level. We've got that gap here. That gap is representative of the F block. The F block in this case would be the 4F block. We have to account for those electrons before we deal with the 5D. Now, on the periodic tables that I gave you, the F block actually has 15 elements in it. There's a blank spot here. Remember that one of these elements, most likely lutetium and lawrencium, but one of these elements actually occupies that first D sublevel electron. So it would have been 4F14, then 5D10 in the case of our gold. All right, any questions here? Yes?
For gold, it still steals the electron from the S level, even the 4F14.
The 4F is completely filled and in a lower energy level. So it's a lot less accessible. Ben?
So if the F level wasn't completely full, would it feel as
if the F level is not completely full, what's actually more likely to happen is that the F will steal from the D. And again, that gets into those exceptions that we are trying painstakingly to avoid. So, we will only deal with the F block when the F block is completely filled or completely empty. We won't deal with any elements that go away from that. So it's either going to be completely filled or it's going to be completely empty. Any other questions? All right, let's talk about ions. Now for ions and ion configurations, we kind of follow the same sort of pattern. The only difference is for negative ions, we're going to add electrons. And for positive ions, we are going to subtract electrons. Now with adding electrons, it actually is really easy because all that you have to do is, let's say that you're looking at element number 34. Well, there's an electron configuration for selenium that we could easily come up with. If we make selenide, element number 34 with 2 extra electrons, all that it means is it's going to have the same configuration as the element with 36 electrons, which would be krypton. So when we're adding electrons, all we need to do is add those electrons to the number and then write the configuration for the element with that number. And usually, when we make negative ions, we end up at a noble gas as a result. And so the noble gas configuration is super easy because it's just a noble gas. There's nothing afterward. So in the case of selenide, I would write that the noble gas configuration of selenide, Se minus 2, is krypton. And that's all I would have to write. That is a noble gas configuration. That is a completely filled energy level. Cations, it's a little bit more complex. For your main group elements, especially for elements with atomic numbers less than 20, we end up in the same spot. We can kind of do the same thing. Once we get that D block involved, it becomes a little bit more complicated because then we have to start looking at energy level. And we start taking electrons from the highest energy level that is available, and then we go down. So for these ones, all of these fit into that first category. Calcium is element number 20. It has no d electrons. So to take 2 electrons away, it would have 18 electrons now. Noble gas configuration for 18 electrons is simply argon. For sodium, sodium has 11 electrons. If I take 1 away, it has 10 electrons. 10 electrons is represented by the noble gas configuration neon. For chlorine, chlorine has 17 electrons. The -1 charge adds another. 17 plus 1 is 18. 18 electrons corresponds to argon. Phosphide ion, phosphorus has 15 electrons. The -3 charge adds 3 more. 15 plus 3 gives me 18 electrons. And so once again, I'm at argon. So for main group elements and for negatively charged ions, this is pretty easy and straightforward. Like I said, it gets a tiny bit more complicated when we have to start throwing in transition metals, when we have to start looking at elements that have d electrons in their outer configuration, in that configuration past the noble gas. Because then we have to look at energy level. And that's where the energy level comes in. So if you were taught to write your electron configurations in that energy level order, it actually makes it a little bit easier because then you can see, okay, the 6s is the highest energy. I'm going to take that one away first. Then I'm going to take away from here. Then I'm going to take away from the next place. The example we give here is with the chromium-3 ion. Here we can see chromium is an S1 exception. Its normal configuration is argon 4s1 3d5. In the other form of the notation, we would see it as argon 3d5 4s1. I need to take 3 electrons away to give it a 3- charge or 3+ charge. So this electron goes away. 2 of these electrons are gone. So I have 3 left over. Argon 3d3 is the leftover. So once we get into elements that have d electrons, we can't just simply move backward. If we did, we would end up with the configuration of scandium, and the configuration of scandium is 4s2 3d1, something completely different than what we actually see for the chromium-3 ion. So definitely be aware of this phenomenon because it's something that is very easy to get tripped up on and make simple but silly mistakes. All right, once again, We'll just do the noble gas configurations. So go ahead, take another, let's take another 4 minutes or so. Write out the noble gas configurations for these ions. Keeping in mind that if it is positively charged and possesses D electrons, you're going to have to skip around the D block to get those electrons out. Go ahead and go. All right, let's see how we did. So the big key here, is that we have to dance around that D block whenever the D block is present, and we are making cations, positively charged ions. And we dance around that D block and we take everything around the D block first. Then we dig into the D block. So for gallium, gallium's probably the one that gave you the most trouble because we had electrons in the fourth energy level, in the P sublevel, and in the S sublevel. So most of you were like, okay, I know I can take away the one from the P sublevel, but I still got to take away two more. If you took them away from the D block, you kind of missed the point. The whole point is I've got electrons in the fourth energy level. I'm going to take those ones away first. So once I took away the P and the two that were in that S sublevel in the fourth energy level, that was the 3 electrons that I needed. All 10 of the D electrons remained intact, remained as a full sublevel, were much more stable that way. And so when we approach it from this standpoint, we can actually start to rationalize why certain kinds of ions are more common in the transition metals than others. Why is positive 2 the most common transition metal positive state? Well, think about what electrons are being taken. The S electrons are being taken. How many S electrons are there? 2. Why is positive 1 a very common state as well? Think about all your exceptions. Silver, gold, copper. Positive 1s make a whole lot of sense there because it's just taking away that one S electron that didn't get to migrate over to the D. So there is some rationality that we can kind of derive and pull from this. So we come now to periodic trends, and we're just about running out of time here. So what I'm going to do is I'm going to make a supplemental video on YouTube. I'll put it in an announcement. I'll send it to you later today. The periodic trends video probably is only about 20 minutes or so to go through all of them. But obviously I don't have that time here today. And if I can convince you to watch it over the weekend and ask questions about it on Monday, if we get stuck on stuff, that'll give us more time to review on Monday and less having to go and do new stuff right before the quiz. So I'm going to ask you to do that. Hopefully that's not too big of a burden for you to do over the weekend on top of the other stuff that you do. But if you run into problems, go ahead and ask questions. Bring those questions with you to our Monday session, and we'll kind of take it from there. So I'm actually going to cut it right there and stop for the day. Have a great weekend. And again, check your emails and your announcements from me. I will let you know when that supplemental video is available. You can watch it on your own time this weekend. Have a good weekend.